Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. In my channel I deal with the different aspects of mathematics, physics, chemistry and some of the related topics. So today I'm going to look at magnets and magnetism, and this falls under a broader category of course electricity and magnetism, which of course is a very relevant area that finds wide application in industrial processes, especially in the electronic industry. So today we're going to look at the basic concepts, which is going to basically assist us have a build-up of the whole concept of electricity and magnetism. And we're going to look at various ways in which we can be able to describe materials as either magnets or non-magnets. And we're going to look shortly into some of the theories which have been advanced in order to explain this specific phenomena of magnetism. Now, in this specific case, then therefore it calls us to define this specific concept of magnetism, whereby we're going to see that a magnet basically is a material that attract, magnets are materials that attract each other. And in this specific sense, we're going to see that there's a specific category of materials that are going to attract one another. And this, if we try to narrow down these specific materials into particular elements from the periodic table, now that we know specific materials, then therefore we are going to categorize these materials that are materials that are made up of specific elements. And these elements, we can be able to particularly list them now that experiments have shown, or analysis have shown, that these materials contain iron, and then they contain nickel and cobalt, which are displaying these specific properties of attraction. Now, in some instances, we're going to encounter this combination of materials, especially the metals elements which I've listed. For instance, what we refer to as nickel, which is an alloy that's made up of aluminium, nickel, and cobalt, which is going to display this specific kind of characteristic of attracting other materials. So in this specific case, these are going to make us this type of what we refer to as magnets. And therefore, from these different characteristics, depending on the intensity of attraction, we're going to categorize these magnets as either strong or weak. And perhaps we can be able to give them two specific categories for permanent, perhaps for what we refer to as permanent and temporary magnets. And the material, like the alloy of aluminium that I've listed, is used to make a strong permanent magnet, of course, and this makes it very widely to be widely applicable in industrial processes. And we're going to see that this concept of magnetic basically has some specific laws which is it's going to follow. And these are some of the laws that we have encountered, especially when we were talking about the concept of charges, whereby we see that some scientists like Robert Milken and Michael Faraday came up with the concepts of describing charges, which were basically the laws of attraction that is going also to affect this concept of magnets. But there's going to be a slight deviation that we're going to see, especially when we're going to give a formula to describe this specific concept of a magnetic field, which is going to have a contrast with the normal definition of other fields like the electric field that we have already seen in one of our videos. So in this specific case, then therefore it follows that from the laws of attraction for magnets, unlike poles are going to attract, we're going to see what we refer to as poles in magnetism, and then we're going to see that the like poles are going to repel one another. So in this specific case, I've mentioned the concept of an electric field, and basically how we can be able to describe point charges from some of the videos that we have done. So I'm going to put a link of those videos in the description box so that they can be able to assist us to contrast these two basic ideas. Now I'm going to illustrate this concept of poles that I'm talking about. So in a sense, we can be able to, of course, give a figurative illustration of a magnet, whereby we have this specific bar that is consisting of two particular ends, which are characteristic, and refer to these ends as N for the north, and then we have S for the south. and these two are referred to as poles. So therefore, whenever we're going to do a reference for poles and say north or south pole of a magnet, then therefore we're referring to these two specific extreme ends. So in this specific case, we're going to have some degree of attraction whenever we have two different magnets which are being brought together in a specific sense, and they're going to follow these laws of attraction that we have mentioned for the two, whereby light poles are going to repel one another, while unlike poles are going to attract one another. So for the first case, if I mention for A and B, so for A, these specific magnets are going to repel one another. So there will be a resultant force that is going to push these specific magnetic bars away from one another. Whereas we're going to see that these specific magnets for the second case are going to be pulled towards one another, and therefore we're going to experience what we call attraction. And for the first case, it's going to be a repulsion in that specific order. Now, if you try to consider this specific case, we're going to see that these forces of attraction and repulsion are going to be dictated by some conditions, whereby if this distance of separation that is in between here is widened, then therefore the intensity of attraction is going to be minimized. Therefore, this is going to play a role in trying to quantify this aspect of magnetism. And therefore, we're going to see that around these magnetic bars that I've given on the board, just going to remain with one, we're going to see that there's going to be an area or the field of influence that is going to be created by what we refer to as magnetic fields. So therefore, there's going to be lines of attraction that are moving from the north pole to the south pole, and these are known as magnetic field lines. Magnetic field lines are the lines of forces that are, of course, are creating an influence around this around this magnet, and therefore it's going to be referred to as a magnetic field. So I've stated that the intensity of this magnetic field are going to be dictated by distance. So therefore, we expect that near these specific poles, the intensity of that magnetic field is going to be more as compared to other distances which are far away from those regions that we have referred to as north and the south pole, respectively. So if you try to look at the other aspect, of course, there are some theories which have been given to explain this kind of attraction that is displayed by these magnets. And one of the theories that we're going to see is going to relate to the concept of electronic theory. But of course, we're going to see that also there's what we call a molecular theory that is going to show why magnets attract one another. And in this specific case, the magnetic theory tried to depict a case whereby if we have a paramagnet, this specific point, and we try to split it in the middle, we're going to have two magnets, whereby this is going to form the south pole and the north pole, respectively. So the theory states that these magnets can be split up to the molecular level, and this is going to explain, of course, the existence of what we call a pair of magnets. Now, in an essence, of course, we said from the study of charges that charges are going to exist as point charges. But for magnets, as we have said, that these are forming poles for the north and south pole. Magnets do not form monopoles, which basically refers to the concept of either south pole existing as an independent aspect or the north pole instead is existing as an independent aspect. But these are going to combine to form a pair, which basically is going to be displayed up to the molecular level. So from the specific concept that we have looked at in basically quantum mechanics, we talked about what we call it the atomic structure. And in this case, from the concept of the atom, we're going to use this why the magnets attract other materials, or attract or repel one another. So if we try to have this figurative illustration of Rutherford's demonstration on the structure of an atom, or the present understanding of an atom, then therefore we're going to see that in the middle here we have the nucleus, And if you have an atom that is having two electronic levels, and then there are electrons which are revolving around this nucleus for the two levels, these electrons are going to experience a spin, whereby as they revolve around that one, they are going to experience some spins. And therefore, this spin are going to play a vital role in the establishment of this, what we call the magnetic poles. In a sense, we had talked about the concept of a spin from the electronic configuration of a different uh, elements, and we had said that electrons are going to have a spin insofar as their configurations are concerned, and therefore this is going to have an effect on what we refer to as a magnetic field. So this is a concept that is being advanced by the electronic theory of magnetism, whereby electrons spin as they orbit, as I've explained. And then we're going to see that the magnetic direction depends on the direction of the rotation of these specific spins. And then for non-magnets, we're going to see that the quantity of the spins which are being experienced, of course, are going to be, dictating whether material is going to display magnetic or non-magnetic property. So suppose we compare two very small particles which are magnetic, of course, which I've said to be particles that can be molecular. So we have north-south, north-south, north-south. So due to the fact that these particular particles are going to attract one another due to the opposite poles facing one another, there's going to be an ordered alignment of these particular particles. So this is going to be, of course, displaying the magnetic property. And in any case, if we find out that these specific materials, the spins in them are going to be disorganized, whereby this one is going to be perhaps experiencing other influence of other particles around them, and therefore this level of disorganization is going to distort this kind of magnetism that is being experienced, and therefore this material is going to be referred to as non-magnetic. So this level of alignment, of course, is going to play a role insofar as the electronic theory of magnetism is concerned, in trying to explain that aspect of attracting other materials in magnetism. So this, together with other ideas, are going to assist us, of course, understand why materials attract one another. And this basically entails the concept of what we refer to as magnetism. Now we're going to have other topics which we are going to advance in trying to explain, of course, how we can be able to quantify these characteristics of a magnetic field that I've talked about as part of our discussion in this video. So this is going to be one of the vector fields that we said that, of course, was part of the vector fields of the gravitational field, the electric field, and the magnetic field in this particular case. And we're going to see how they are related to one another and how we can be able to quantify them and the various differences that we're going to see between them. Now, for instance, for the magnetic field, it's going to display a different properties. We have said that it cannot exist as a monopole or monopoles, a condition which, of course, can be able to be achieved by charged particles or electric charges. So catch us in our next videos. We're going to look at the magnetic field and try to explain how this magnetic field can be described in terms of perhaps an illustration or a formula. So that is it for now, guys. Bye. God bless you.